very little time, and the syllabus was too large, too big syllabus. We have a very big syllabus. So this one, two chapters we have completed: moving charges and magnetism and matter. This electromagnetic induction, if we try, we can complete this chapter also. Okay, let's start it. What is magnetic flux? Electromagnetic induction. So the first topic is magnetic flux. The magnetic flux through any surface placed in a magnetic field is the total number of magnetic lines of force crossing this surface normally. So if we have a closed surface and the total number of magnetic lines of force which crosses that surface represents what we call as magnetic flux. Magnetic flux is the total number of magnetic lines of force which passes through a surface normally. Okay. Now, magnetic flux is a scalar quantity denoted by phi or phi b. If a uniform magnetic field B vector passes normally through a plane surface area A, as shown in figure A, then magnetic flux through this area is phi is equal to BA. If the field B vector makes angle theta with the normal drawn to the area A, then the component of the field normal to this area will be B cos theta. So we are having two different orientations of a loop. So first is this. If we have a loop like this and some magnetic lines of force are coming to the loop like this and crossing it like this, like this. So this is area, this is area, and these are magnetic field lines, B vector. So what is the direction of area? Always remember this, that the direction of area, the direction of area is always normal to itself. So direction of area is always normal to itself. So what is the direction of area? Direction of area is represented by this n cap. That is, this is area vectors direction. Area vectors direction. But what will happen if the field? What will happen if the field is not? What will happen if the loop is not? Magnetic field is not normal or perpendicular to the area. Then what will happen? Look, this is figure A. So in such case, magnetic flux phi is equal to magnetic field into area of cross section. Phi is equal to B into A. But if this is like this, loop is like this, and a magnetic field is going like this, so what is this? This is n cap. This is direction of this area vector, normal to direction of. What is the direction of area vector? Area vector's direction is always normal to itself. So this is n cap, this is B vector, and what is the direction? What is the angle between n cap and B vector? It is theta. It is theta, and area of this loop is capital A. Area of this loop is capital A. Now, this one is figure B. Figure B. The SI unit of magnetic flux is Weber. SI unit of magnetic flux is Weber. Is that clear to you? In this case, phi is equal to, we always take the direction of magnetic field along the area vector. So direction of magnetic field along this line will be B cos theta. So phi will be equal to phi is equal to B cos theta into A. B cos theta into A. So phi is equal to B A cos theta. What is BA cos theta? It is B vector dot A vector. This is called dot product. B vector dot A vector. So what is magnetic flux? Is this clear to you, Anusha?
Yes, sir.
Okay. Now the next topic is electromagnetic induction. This one, what this topic says, the phenomena of production of induced EMF and hence induced current. The phenomena of production of induced EMF and hence induced the phenomena of production of induced EMF and hence induced current due to a change of magnetic flux linked with a closed circuit is called electromagnetic induction. Electromagnetic induction, the phenomena of production of induced EMF and hence induced current due to a change of magnetic flux. Whenever in a circuit magnetic flux changes, whenever magnetic flux changes in a circuit, then it always produces an induced current. It always produces a current whenever magnetic flux changes in a circuit. So as long as magnetic flux keeps changing, current keeps producing, current keeps on getting produced in that circuit. So there are three laws of electromagnetic induction. A is Faraday's laws of electromagnetic induction. So Faraday has given two laws of electromagnetic induction, and the third law is given by Lenz. Lenz was also a scientist. So A is Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. Faraday's laws of electromagnetic induction. First law, whenever the magnetic flux linked with a closed circuit changes, an EMF and hence a current is induced in it, which lasts only so long as the change in flux is taking place. This phenomena is called electromagnetic induction. Whenever the magnetic flux linked with a closed circuit changes, an EMF and hence a current is induced in it, which lasts only so long as the change in flux is taking place. This phenomena is called electromagnetic induction. So, Faraday's laws of electromagnetic induction. So, first law is that as long as the magnetic flux keeps on changing, till that time only, as long as the magnetic flux keeps changing, till that time only current gets produced. After that, if magnetic flux stops changing, then current stops getting produced. Is that clear to you? First law.
Yes, sir.
Okay. Now second law, the magnitude of induced EMF is equal to the rate of change of magnetic flux linked with the closed circuit. Mathematically, so this one is second law. Magnitude of induced EMF is equal to d phi by dt. Phi is magnetic flux and d phi by dt is rate of change of magnetic flux. Now, B part. This one is first law, this one is second law. So these two laws were given by Faraday. B is Lenz law. Lenz, Lenz's law. Lenz law. This law states that the direction of induced current is such that it opposes the cause which produces it. It opposes the cause which produces it. That is, it opposes the change in magnetic flux. Anusha, give me 1 minute time. I am coming back. Anusha?
Yes, sir.
Can we have a class tomorrow?
Yes, sir.
So which time are you free for tomorrow?
I don't know, sir. What time are you thinking of?
You tell me the time, any time for which you are comfortable.
I'm thinking all day, basically.
Any time.
Mostly like from the afternoon onwards.
Okay. Uh, so after 12 p.m. of Dubai time.
Can I inform you later on? By tonight?
Okay. Okay. By tonight, you just drop me a message. Okay. Let's do one topic. Let's do one topic.
Mm.
This is mathematical form of the laws of electromagnetic induction. Expression for induced EMF. Expression for induced EMF. This EMF is getting induced. Induced means this EMF is getting this EMF is getting produced. As long as the flux keeps on changing, as long as the magnetic flux, keeps on changing, the EMF, as long as the magnetic flux keeps on changing, the EMF keeps on getting induced. The EMF keeps on getting produced. Okay, so now what is this Lenz law? According to Faraday's flux rule, magnitude of induced EMF is equal to rate of change of magnetic flux. Expression for induced EMF. So magnitude of induced EMF E is equal to d phi by dt. Magnitude of induced EMF E is equal to d phi by dt. Taking into account Lenz rule for the direction of induced EMF, Faraday's law takes the form E is equal to minus d phi by dt. E is equal to minus d phi by dt. Minus d phi by dt means uh, Lenz law states that Lenz law states that the direction of induced current is such that it opposes the cause which produces it. It opposes the cause which produces it. So the cause which produces induced EMF is d phi by dt. So induced EMF opposes the cause. The cause is this d phi by dt, which produces it. That's why this negative sign is here. And we can understand it through the illustration of Lenz law also. Look onto page number 4. Illustration of Lenz law. Illustration of Lenz law. Let us suppose that there is a coil like this. Let us suppose that there is a coil like this, and there is a magnet like this, North Pole and South Pole. North Pole and South Pole. North Pole and South Pole. So when we move this magnet near this loop, then what happens? Actually, there is no battery connected to this circuit. This is just a circular loop of wire. And what is this? This is a galvanometer. Galvanometer always indicates the direction of current, always indicates whether the current is going, whether a current is present in it or not. Okay, so when this magnet goes near this loop, then north pole induces a north pole here, induces a north pole here, and when north pole develops here, then north pole means current will be in anti-clockwise direction. I told you earlier also that north means n, and when we speak n, then what comes from our mouth is n means anti-clockwise. So we keep in mind it like that, because north is coming near this, so it is developing a north pole here, and this north pole is producing an anti-clockwise direction current here, current in anti-clockwise direction. And if we watch it from here, then if anti-clockwise current is going here, then if we watch it from here, then we will be observing that current is in clockwise direction. So this will become a south pole. Now, if north pole develops here, then what this north pole is going to do? This north pole is going to repel this north pole. This north pole is developed here because of what? Because of this magnet, because we are bringing magnet near here. So this is the cause, this is the cause, and this is the and this is the result. So this cause is producing a north pole here, and now this north pole is repelling this north pole here. Okay, so induced EMF or induced current in a loop is like that. It opposes the cause which produces it. Understand? Is that clear to you? North pole is developed because we have brought this north pole close to this loop. Now a north pole is developed here. Now this north pole is opposing this north pole. It means that the induced EMF is such that it produces, or induced EMF or induced current is such that it opposes the cause which produces it. Now if we do now if we move it like this, then what happened? See, now if we move this magnet away, so when we are moving this magnet away, then what will happen? A south pole will develop here. South pole means current will go in the clockwise direction. Current will go in the clockwise direction. Now this south pole, now we are moving this magnet away. So when we move this magnet away, then a south pole develops here. Now this south pole is going to do what? Now the south pole is going to attract it, because south attracts north. So when it was coming near to this loop, then it was repelling it. Now it is going far away, now it is attracting it, means it is opposing, it always opposes the cause which produces it. Now it is going, we are moving it in this direction, now this south pole is attracting it. It means that it always opposes the cause which produces it. This is the illustration of Lenz's law. Is that clear to you, Anusha?
Yes, sir.
Okay. Now we have two derivations, motional EMF from Faraday's law and motional EMF from Lorentz force. These two derivations we will do tomorrow. And power I think power is not in syllabus. Power methods of generating induced EMF. Yes, it is in the syllabus. We have to do it. And after that, self-induction and mutual induction. Anusha, very small syllabus is left. And if I take a 1.5 hour class tomorrow, na, then it will get finished. Very little portion is left. Okay. So you revise properly the initial two chapters, moving charges and magnetism and matter. Now only 3 or 4 topics, only 3 to 4 topics are left in this chapter. So we can easily cover the syllabus by tomorrow itself. Okay. And here it is 11 p.m. Right now it is 11 p.m. in India. So most probably I will be awake by the next 1 hour. So by the next 1 hour or 1.5 hour, please tell me what time, after which time I shall keep your class tomorrow. Okay.
Okay, sir.
Okay, Anusha. Okay. Good night.